last class we ended by talking about some of the assumptions that we have with ordinary least squares regression. And the big one is, of course, that you have variables that have a linear effect. So that as you increase x, there is a uniform and consistent change in y. And this goes back to high school when we learned about slope. A 1 unit change in x results in well, then it was m, but today we call it beta, a beta unit increase in y, whether that's positive or negative, or if there's no effect, a 0 increase. The example that I've used to demonstrate this have been things like, what was it, birth rate. And we haven't really dove into, well, what do you do if you have a different type of dependent variable? See, we've just been focused on what does the model give us and how does it come about. We know that x increases and then therefore y changes as well. Well, OLS works best in a limited set of circumstances. First of all, OLS works best when you have a dependent variable that is, I'm going to put this in stupid quotes, scare quotes, continuous. Ordinary least squares, because we're talking about changes, and even sometimes fractional changes in y, it's really designed for a continuous variable, one that ranges a lot. Ideally, it would have a full range of values. So probably the best continuous variable we could use would be something like temperature, right? Because temperature really doesn't have, it does theoretically have a bottom, right, with absolute 0. We can never achieve it, but theoretically there's an endpoint. And then you can get really, really, really hot, right? So temperature has a good range of values that are almost infinite. The other thing that works really well with ordinary least squares is money. Because you can have tons and tons and tons of money, but you can also have tons and tons and tons of debt. Right? So money is another thing that has a very good range. But we're political scientists. We don't always have a dependent variable that has a large range. We can create dependent variables that have some range to them. Back to our old friend feeling thermometers. That has a 0 to 100 range. It's 101 potential values you could have. That's great. But we saw that when we looked at the data, really how many values are there of a feeling thermometer that people actually use? Do you remember that from the beginning of the semester? When we looked at Hillary's range of values on the feeling thermometer? It is 100, but how many did people tend to choose? Yeah, not even 10, right? There's like the zeros, and then like there was one in around 30-something and one around 60-something, and then people kind of liked her at 70-something. Right? So there were really only a handful of values that you actually used. And I think Tom and I came up with like buckets for them, right? Like, well, these people are the haters, and these people, right? We had these different categories for them. But what would you do if your dependent variable only had 2 options? Right? What if we took that feeling thermometer of Hillary Clinton? We have some independent variable here, x. Let's call it income, because again, we like variables that go in a range. But our dependent variable is now voting for Hillary. going to do one more trick that we usually do. Usually when you have 0, you don't actually put it at the very, very bottom. You put it up a little bit. So, and we have, in votes for Hillary, probability that respondent voted for Hillary. Okay. Where are our dots going to be? They're either going to be at 1 or 0, right? So they're either going to be like that. Anybody have a problem with this? What, Joey, you don't think there's a slope? So what Joey's saying is that the best line is going to be like this? You don't think so? All right. So this is one of the problems, right? So here's an example. You have these dots. If you were actually to do OLS, the line would, you know, we could have this potential of it doing that, right? You have also the potential of it doing this. What is this line usually? It's no slope, but how do we know what its value is? What's the best expected guess of your y variable, having no other information at all? That's the slope. That's the high school version of slope. This has no slope. We've done this before. No, the y-intercept is when x equals 0. Yeah, it's the average, right? So this is our y bar line. Now, what would the average be if our variable is a 0, 1 variable, and it's either 1 or 0? What is that average going to be? It won't be a half because, well, we could have a half. It could be 0.5. But what functionally is it going to be? Think about this, all right? It wouldn't be the value of how many people vote for Hillary. It would be the close. No, the third P word. It would be the proportion, right? So that's what your y hat bar is going to be. It's going to be the proportion or the probability, percentage, whatever you want to call it. I like proportion. It'll be the proportion of voters that were Hillary voters. So instead, we clearly have violated one of our assumptions. And that assumption that we violated is this idea of being linear, that the relationship between x and y is one that is linear. So we have to do something slightly different. And what we're going to do differently is we're going to move away from sort of let's call it a geometric explanation, where we're talking about slope and rise over run. And instead what we're going to do is we're going to use another framework that we have, that we use quite often, that we know quite well, and that's probability theory. What we have here is, here's our OLS line. What we have here is a line that is estimated from something called maximum likelihood estimation, or MLE. And what MLE does is it focuses on probability theory. It doesn't rely upon anything that's linear. Now, your data could be linear. And MLE is so good that it would still find the right outcome even if you were using it on something that OLS is better for. I'll get back to that in a minute. So instead of having a line, a slope line, that gives you a predicted value of y, right? Instead, what we have here, this, is in the shape of, we call it an S curve. And what we're doing is we're predicting the probability that y equals a value. In this case, 1 or a vote for Hillary. So instead of having a slope, now what are we going to have? What are we going to be trying to predict? Because beta no longer is a slope, right? We're getting rid of the slope. Slope requires a straight line. Instead, we're going to be calculating betas that are going to give us what? The answer's already up there. Nope. The probability, right? The probability. That's what it's focusing on. The probability that y, our vote choice, equals 1. So we're shifting back to probability land. Because why is probability so great for this? Well, first, it's we only have really two choices. It's bounded between 0 and 1. And it's focusing on the outcome. It's focusing on either success or failure. This is how maximum likelihood was explained to me a number of years ago. And it sounds a little silly, but you just got to stay with me for a minute. Okay. Imagine we have a set of data, and we need to find the highest point on our little mountain here. Does everybody see where they think the highest point is? Think you know where it is? In order to find that highest point, we drop a little guy on the mountain. Okay, we'll give him a parachute, if you insist. That's me drawing a parachute. And he lands safely down here. Now, who remembers calculus from high school? Nobody? Oh, nobody took calculus? You don't remember it? I know that calculus is good for one thing and one thing only. Finding the slope of a line on a curve. Does that make sense? So if you want to find the highest point on a curve, what are you looking for using calculus? Not area. Something we've been talking about a lot. Like, how do I know that this point here is not the highest point? Because that point has a slope. The highest point on that little bump is what? Has a what for a slope? It's flat, right? It has a 0 slope. So if we land the little guy down here and he starts climbing up the mountain and he gets to the top, is he going to know that he's at the top of the entire mountain? Right, he's only going to know I'm at the top of a point. But does he know that there's more mountain ahead? Well, if he can see, yeah, right? You can see the hump, but he can't. Because if we could see, then we wouldn't have to drop the little guy on the mountain to begin with. Right? He's going to have to keep going. He's going to have to keep searching. He's going to have to keep going, right? He's going to have to keep going like this. He's going to also have to go this way. So if we just sort of blindly take our data and ask ourselves, all right, which is the highest probability, we can only, using calculus, understand that by assuming that when we've reached a slope of 0, we're at the highest point. But you don't know that unless you go along the entire little mountain and check out every point along the entire range of values. The reason that calculus is handy, again, because it tells us the slope of a point on a curve, but we need to have a different framework, right? This is still the geometric framework, where we're thinking about, all right, what's the slope of this point? Is it the highest point? That's all geometry. We got to get away from that, because that's not going to help us, because we need to be talking about things like probability. So instead of taking this sort of geographic approach, where we're going to send the little guy going along our entire data distribution and looking for the highest point, we're going to do something else. We're going to take our data that we have and we're going to look at it and go, what process is most likely to have generated data that looks like this? Okay. What process can give us two outcomes? A yes or no question. What else? Coin toss. Okay, so let's flash back to coin toss. When we were doing a coin toss, were we using our normal distribution? We weren't, right? There was some other distribution that we were using. Anybody remember what that was called?
Was that chart you made, the table?
No. It's a binomial. Well, it turns out the binomial distribution is great for situations where you have two outcomes, like heads and tails. Why? Because when you look at the distribution, it's an S-shaped curve. So, we know, first of all, that maximum likelihood estimation is probability based. We also know that with maximum likelihood estimation, you can change the distribution. You can change the shape of the distribution. You don't have to use the normal distribution. With ordinary least squares, difference of means tests, we're using either the normal distribution or student's t. We're using a bell-shaped distribution no matter what. The next step in your statistics education journey is to learn, or at least remember, that there are other distributions out there that have slightly different shapes. What's that look like? Looks like a slide. Does it look like half of anything? No. Half of a parabola is a U. Parabola. Had an Australian friend. He always said parabola. Aluminium. It's half of a bell curve, right? You know why it's half of a bell curve? Because this one only has positive numbers. It doesn't have negative numbers. It stops at 0. It's known as a Poisson distribution. Because we have situations where you only have a 0 to positive outcomes, like a count. The Poisson distribution came from a study of, and I love this, horse kick deaths in the Russian army. Armies keep track of things like casualties and deaths. A casualty is not a death. A casualty is an injury that removes you from the battlefield. A death is a death. And one of the things they were curious about was whether or not it was worth having horses. The problem with horses is that when they kick you, you die. So is that a piece of equipment that's around that is sort of useful? So somebody, I can't make this up, did a study on how many deaths can you expect in a war if you have horses around. And then you have to decide if that is an acceptable amount of deaths due to, I don't want to call it friendly fire, but, due to horses. Well, that sort of distribution doesn't require a full range of values, right? Because if you have horses around, there's no opposite of, being kicked and then dying, right? There's no negative. You can't have negative deaths, like births that come about because of horses being around. You can't get more soldiers by having horses being around. They're not magical unicorns or anything that poop soldiers. They're not. No, they're not. Okay. So when we're analyzing horse kick deaths, a normal distribution isn't going to work for us. But it turns out that the distribution of the data sort of implies that the more horses you have around, the more likely you are to have horse kick deaths. Which would make sense, right? The funny thing is that we're still going to model the shape of this distribution. There's something known as a zero inflated Poisson distribution, or a ZIP. And a ZIP is where that zero category, where you have no deaths, it's really, 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 really high. Because horse kick deaths are very rare. They're even rarer today when the United States military has like 4 horses. So if you were doing horse kick deaths per year, you would have a bunch of armies that would say, no, we didn't have any horse kick deaths this year. Think about police agencies. Does coastal police have any horses? I don't believe so, right? Does the NYPD have horses? Yeah, they do. Which one is more likely to have a horse kick death? CCU PD or NYPD? All right? But the number of forces out there that still have horses is really low, right? So if we were to go and we were to catalog every law enforcement agency and say, do you have any horse kick deaths to report? When they're done laughing and we're done explaining to them what we're trying to do, there would be a lot of zeros. So that would be a distribution. That would have a very tall start because you're going to get mostly zeros. And then it's going to get really short really quick. That's a zero inflated Poisson. Okay. So what are we doing here? Well, with maximum likelihood estimation, we're looking for a process that still minimizes errors. So that's still the same. In OLS, the magic line was to minimize the space between what was predicted and what was actually observed. So that stays the same. We're still trying to minimize error. We're still trying to get the line that has the best fit to the data. Still trying to best fit the data. But it just so happens that for some data sets, a straight line is not the best line. What MLE does is it tries to create the best set of parameters. Now, a parameter is just is a coefficient. It's a statistic. It's our betas. Seeks the parameter values that are most likely to have produced what we have observed. Now, within this maximum likelihood estimation framework, we can give it a hint. We can have an idea as to what is the distribution that would give it the best shape. So when I'm doing a model that involves a count, I'm looking at the Poisson distribution. I'm going to actually look at my number of zeros to see if the zero inflated Poisson fits better. I'm also going to look at something known as the negative binomial distribution. You have options. You have a lot more options than you do if you just stick with a dependent variable that has a huge range and you are going to do OLS. That's the great thing about maximum likelihood. Because our dependent variables, well, they can take a whole bunch of shapes. We talked about count. So we can count the number of horse kick deaths. We can count the number of children a person has. We can count the number of times that a member of Congress files a discharge petition. We can count the number of times that a justice dissents on an opinion in a court term. Right? Counting is a really easy dependent variable to create. Lots of opportunities for dummy variables as dependent variables. Did you vote? Yes or no? Vote choice. Did you vote for the winner? Yes or no? How did a member of Congress vote on a bill? Yes or no? Abstentions, we can throw abstentions in there. Most times we just throw them out of the data set. Or count abstentions as no votes, depending upon your theory. So we can have 0, 1 variables. We can also have ordinal variables. Where we have categories of outcomes. Strength of your opinion about abortion. We can create a 5-point scale, right? 5 different categories. We can also, if we wanted to, do a nominal dependent variable. Probably should put Clinton first since she got the most number of votes, but Johnson, Stein, other. One of the first times that I encountered an MLE model that would do nominal outcomes, we were trying to predict who people would have voted for if Ross Perot didn't run against Clinton and Bush in 1992. Because what you actually have is you have multiple options when you go to vote. So you could have voted for Trump, Clinton, Johnson, Stein. In South Carolina, at least, there were 3 other candidates. You had 7 options when you went to vote. So we could do that. We could also have dependent variables that are related in terms of time. These are known as duration models. And they're really popular in the medical field. Because we're going to give somebody a drug, and we're going to see how long they live. They have different names. Duration models is the general one. The medical field likes to call them survival models. How long does somebody survive after receiving a treatment? There's also another way of looking at it. They're also referred to as hazard models. Duration is probably the most general one. So how long, time is it's sort of continuous, but you can't go backwards in time, right? So it's only can be positive. You could also have dependent variables and that are responding to multi-levels. So let's think about your success in this class. We would have class level variables. What would be some class level variables? No. Variables, independent variables. We're explaining student success in math classes. All right, that could be one, right? Attendance, right? Level of effort, okay? So those are a couple of class-specific variables. We could also have individual level variables. So what might be different amongst you as individuals? All right, you could do that. How about how well you do in math, though? How about your math score on your SAT? How about the number of high school math credits that each of you accumulated? Right? Like whether or not any of you took calculus, like she did. Right? So there could be individual level variables too. We can model that. We can say, listen, not only do we have a bunch of differences on our in our independent variables, but those independent variables themselves are two different classes or levels. And you can do multi-level modeling. Well, you're going to have to create a distribution that is no longer a curve, but it's actually a three-dimensional blob. Yeah, you really got to light a candle and sniff the incense on that one. All right? It's kind of like a wave. But people do it. And of course, you can do a continuous variable. Okay. Some of you are going, Jesus, this looks really useful. Couldn't we have learned this stuff? Yeah, we could have, but you needed to do all the baby steps first. Because with maximum likelihood estimation, there is so much difference in the exact distribution that you use, but fundamentally they're all the same. When I'm doing a model that has a dependent variable that's a 0-1 variable, like whether or not a judge votes to extend rights to a social minority, I really only have a couple of options. One is known as a logistic regression, or a logit, and that has a logit distribution. And the other one is a probit. The probit actually is a version of the normal distribution. But no matter which model I run, a count model, a time series model, an ordinal model, a multi-level model, I'm going to have the exact same thing. I'm going to have some version of a parameter that tells me the effect of the independent variable. It just so happens that in ordinary least squares, that's a slope. Rise over run. With maximum likelihood, they tend to be probability based. Probability based creates betas that are odds ratios. We're talking about, is there an increase or decrease in the probability of your success? And if so, what are the odds? So you're still going to calculate some parameter, some coefficient. And the second thing you're still going to do is to see whether or not that coefficient is 0 or not. Is it 0 or not? Is it likely that given our sample, can we produce this parameter with our data? Okay. Here is an example predicted event probability with confidence limits. Okay. I can't remember what this example is, but the independent variable is age. Let's call it death. All right. What's the probability that you die at a certain age? Don't judge me. But when I had my first kid, when I had Abigail, I actually looked up the actuarial tables for females to see what the probability of her death was with each birthday. My daughter. So when Abigail turned 2, I wanted to know how much the probability of her death changed. I'm weird. I will fully admit that. But we have that information out there. It's called being an actuarial, and that actuarial, not with a U, with an I. And insurance actuarials are the ones that determine how much to charge you for things like life insurance. Because the insurance company has to have enough time to invest the money that you pay in to accumulate the value of your policy. So they need to figure out how much to charge you so that when you die and they give you $200,000, that they've actually earned more than $200,000. Okay? So what do we have here? Well, here's a model with age. Let's call it probability of death. Okay? And what we're going to do is we're going to have our S-shaped curve. So what happens to your probability of death as you increase in your age? Probability goes up. And we can get actual values, right? We can get predicted values along this curve. So it looks like in this data, I'm not sure what these are, but let's ignore these two, right? So with this data point at 25, still alive. This data point at 35 was still alive. This data point at 45 still alive. Looks like somebody died in their 70s. Not sure why these two are up there, but whatever. You can tell that they're on their way to death. Let's just go with that. So we have the line. We're still going to predict it. And you'll also notice the shaded area. That's our 95% confidence interval. Right? Again, some of the same things that we've learned with ordinary squares you keep when you do maximum likelihood estimation. But this is a whole nother class. And I'm done.